Blue. Purple. Blue.
Yellow.
Orange. Purple.
Yellow, orange. What other colors?
Purple. A rainbow.
Purple. A rainbow. I've never seen it black in the sky.
At night.
At night when it's really dark. That's true.
Yep.
So I want everybody to talk to the person next to them. We want you in pairs. And we're going to give you just a couple minutes to talk and to come up with the answer to the question, why can we see different colors in the sky? Just whatever you think. So talk to the person next to you. We're not going to answer yet. We're going to give you about 2 or 3 minutes to talk, and then we'll ask for some answers.
Yeah. We're doing it anyway. I don't know, like, I believe. No. I really like that one.
Ready?
Yeah.
Okay. Come back, please.
Let's see if we can get a couple volunteers to share what you're thinking. We're going to let your teacher pick a group of pairs to share what you're thinking.
Sit back and sit down. Like, there you go. Yeah, just there you go.
It's because the atmosphere and the sun and the sun's light, yes, you can change the colors.
So the atmosphere changes the color of the sun's light?
Well, yes.
Okay, that's a good answer. How about
Want
another?
another volunteer? Would you like a second volunteer?
Sure.
Okay. Someone from the back. One of the people I talked to.
We put sun, dust particles in the atmosphere.
What does that, explain to me what you mean by that. That's a good answer.
Well, I know dust particles. We learned that from my old class, and then sun. It usually has something to do with the sky since it's kind of pinkish. And then atmosphere might change the sun's light or something. So once it goes through something color light. That's all.
All right. Do we get one more volunteer?
Anyone else?
Too many people.
Okay, go ahead.
It was if you're counting like certain kinds of light, UV index light is purple,
Okay.
and also after a rainstorm, sometimes rainbows can appear in the clouds, so it's making it basically endless possibilities of colors.
Okay. Good.
And sometimes in the afternoon, the sky can change color from blue to purple to pink to orange to egg.
Why? Why in the
They can-
afternoon?
What?
Why? Why did you say in the afternoon it can change?
Because the sun goes down in this specific part of the earth, and the point that we're seeing it makes the sky change colors.
Okay. Cool. So let me ask a general question to all of you. What happens to light as it travels from the sun to Earth where we can see it?
It denses.
It bounces?
It denses. I think it dims.
Okay. Someone off screen, I had someone say it dims.
It dims.
Yeah.
It bounces, it dims. Anybody else?
It cools down.
It cools down. Okay. Does light pass anything on its way to Earth from the sun? Does it go passing anything?
What does it pass?
Other planets.
Okay.
Atmosphere? It passes the atmosphere. What is the atmosphere?
The gravitational pull around Earth that gives us gravity, makes us not float away into space.
So the atmosphere keeps us on Earth. Okay?
It passes layers of gases.
Layers of gases. Okay? Okay. So, let me ask you a question about the atmosphere. Is there anything different between what's in space and what's in our atmosphere?
Is there anything different from space than what's in our atmosphere? Anything different in outer space?
Space is colder. There's no gas in space at all.
There's nothing in space.
Anti-gravity.
No oxygen.
No gravity.
No gravity.
No
Okay.
No air.
Actually, we don't. Yeah.
So, let me go back.
One side of the space.
Let me go back to one of the answers I got, and one of your classmates said that light passes layers of gases as it goes through the atmosphere. Do most of you agree with that?
Yeah.
So, how do scientists know what kind of gases and how much are in the air? How do scientists know that?
How do scientists know what gases and how much are in the air?
Because they measure the amount of pressure that's in the air.
Did you catch that?
Yes, they measure pressure in the air. Okay. Anybody else have an idea? Satellite? Okay. Moon. So what we're going to do next is Ginger is going to demonstrate for you what happens to light as it travels through the air. So I want you all to focus on Ginger in the purple shirt, and we're going to do a demonstration today.
Hi. Okay. So I'm Ginger Butcher, and I work at NASA Goddard Space Flight Center, and I work with the Atmospheric Chemistry Mission, the ARA mission. So it's the satellite that looks at the chemistry in our atmosphere. So what we're going to do is a little experiment today to see what happens to light as it travels through our atmosphere, the type of things that could happen. Do we have the data sheet? Are you guys going to fill in the data as we do this? Excellent.
Cool.
Okay, so I'm going to go ahead and get started and take the measurements. And let's see. First, we're going to show you the setup here. So here's our circuit. We have power, a little red light, and it snaps together to a light sensor. And we have a number readout. Can everybody see the number? That number? Okay, great. So essentially what happens is the number is going to change depending on how much light is hitting it. So this is sensing light energy. Okay? So our experiment is we have a bottle here, and it's full of water, and the water represents the air in our atmosphere, okay? And what we're going to do is we're going to see what happens as light from the sun travels through the atmosphere to the surface of the earth, okay? So we're going to take two measurements, one on the surface of the earth on the bottom here, and then one on the side. So is everyone ready? We're going to do our first trial. And there's what's called no drops, because we don't have any drops of stuff in our atmosphere right now. It's all clear. So we're going to look and see how much light gets to the surface. So what's the number reading?
99.
Excellent. So that's as high up as this number bit will go. So that's our first reading for the bottom. Yeah, so it's actually the second line. I always do this backwards. Okay? Now, how much do we think that the light that we get up here, if we take a reading on the side, is it going to be higher or lower? Or the same?
Higher.
Okay? Let's check. What's our number?
8.
8. All right, so that's a reading on the side with no drops. Okay, so now we have a little pipette with some creamer. Now we know that we got some answers. It says the atmosphere is not completely empty, right? We have air, we breathe, oxygen, and so forth. So we're going to put something in our atmosphere here, okay? I'm going to count out 5 drops, okay? Our first trial has 5 drops. 1, 2, 3, 4, 5. All right. Give it a stir. And so let's see. What do you think will happen to our reading on the bottom?
It'll go down. Now.
It'll go down? Okay, let's check it. I got to get the highest reading I can get. It's like 45.
Mm-hmm.
Okay. That's the bottom for our trial number 2. It's 5 drops of milk. Let's go with the next reading. This is the side. It's like 12. What happened to the number?
It went up.
All right. Well, let's see what happens. We continue doing this. All right. More stuff. We're going to add another 5 drops, so this will be a total of 10 drops. 6, 7, 8, 9, 10. All right. So the bottom, we think it's going to go what? Up or down or stay the same?
Down.
Down. All right, how low can it go? 24. Okay. I think I just put the flashlight in the water.
Uh-oh.
All right, and this next one, is it going to be more, less, or the same on the side?
More.
Whoa. 20. All right, so that was trial number 3, right?
Yeah.
All right, let's do our next one. All right, it's 11, 12, 13, 14, 15. All right. We all guess what? The same, higher, lower. Let's see. 15. All right, and then the next one on the side. Wow. 28. 27, 28, somewhere there. Okay, so this is our last one. That was trial 4. Doing this right? Debbie, you tell me if I'm messing up.
I will.
All right. We're at 16, 17, 18, right? 16, 17, 18, 19, 20. Okay. We got our sun, our light here. Okay. There we go. That's the highest number I can get. I'm going to take this off for a second. All right, we're going to try this over here on the side. And looks like 30. That's our last one.
Yep.
Okay, so essentially what we were looking at was if light travels through the atmosphere using water as an analog, to see what's happening, what's changing, what's getting to the surface and what's not. Why don't you go ahead and, because you guys have the graph there, and I think we have some time, go ahead and graph the data on the graph below. Do you all have that?
Yeah.
Okay. And I think what you do is you graph the readings from the side. You put a little triangle. And then the readings from the bottom, you put a circle.
Can you see that?
Or 2 different colors.
Yeah, where we go?
That's about
This music,
How are we doing on the graph?
Good. Good.
Let me know when you're done. How many people have their graph complete? Give me another minute.
Is there music playing somewhere?
Yeah.
Yeah.
Oh.
Got it?
So looking at the graph,
Just another minute. 1 minute? Okay. 1 more minute, okay?
yep,
Okay.
take your time. Are we good? All right. So I want you to look at your data and tell me what you notice. What did you notice about the numbers on your chart, and what do you notice about your graph?
The side was increasing, and then the bottom was decreasing.
Okay, so the side was increasing and the bottom was decreasing. When you do that on a graph, what does your graph look like? So the bottom line started where?
What does your graph look like?
And near the top, right? And then the numbers went down. And your side graph, the numbers start where?
Towards the bottom.
Towards the bottom and go up. So your graph almost looks like kind of an X, right? So what's happening to the light?
You're cutting in and out. We didn't catch that.
Okay. What's happening to the light? If the sensor is reading how much light can be detected, what is happening to the light?
What's happening?
I didn't hear that.
It's brighter.
The light gets brighter. What?
It gets, the light gets brighter.
Michael, we seem to be getting a lot of feedback or something on the microphone. I don't know where the microphone is sitting.
Oh, let me see if I can move it around. Let me close the window because it might be coming from outside.
Okay.
Is that better?
Yeah, that's great.
Yeah.
Okay, the young lady who just had her hand up.
The light gets brighter or darker.
When?
At the
Where's the light getting lighter? Right in your card.
Okay. Why do you think that's happening? Does the milk have anything to do with that? The creamer? What's going on in that bottle? Go ahead. I see one hand up, young lady.
clogging up, and so
Stand up and say loud.
it's kind of like clogging up, and so the light can't travel as much.
So, okay, it's clouding up?
No, clogging.
Clogging up. What's clogging it?
Drops are clogging up the water, and it's like it makes
Drops are clogging up the water.
the drops are like they're kind of like making the water kind of looks like it's polluted. So the light can't really go through because it's not clear anymore.
Sarah, what did you want to add?
The light is getting caught in the density of the water.
Getting caught in the density?
Yes, the water is getting thicker because of the drops, and the light isn't traveling through it as easily as it used to when there were less drops.
Okay, I didn't hear all that. Could you repeat that, please?
The light isn't traveling through the water as well as when there were less drops. As she's gradually adding drops, the water became thicker to the point where the light couldn't travel very well.
Okay. So,
So why is it getting brighter on the top? Why are we getting more light on the side reading? If it's thicker and the light's just going in there and getting stuck.
The light might be bouncing off from the water to the side, so
bouncing off the water?
yeah, the light might be bouncing off the water to the side.
Okay.
No, I'm getting the feedback. Give me a second. I'm going to try to fix this. I apologize.
No problem.
Try again.
The light might be bouncing off from the water to the side instead of going straight down.
But when we had just water in the bottle, we're getting heat coming out of the side.
Because there was less water, so it could go in there more easily. And once it got thicker, it was not as much, so more water would go to the side.
Interesting.
There's another spot over here.
All right.
But
Maybe the drops sink to the bottom of the bottle, and that makes the bottom decrease. Right?
did you catch that?
Yes.
Okay.
Okay, so you think the drops are sinking to the bottom, and so the bottom is decreasing in the amount of light and the side is getting more?
Yeah.
Okay, I saw one more hand back there.
Maybe the light is bouncing back.
Gotta be louder than that.
Maybe the light is bouncing back because there is a lot of light on top and side. There was stuff in the bottom, which means there's a
So you guys are talking a lot about the light bouncing back and how the drops move through the water. Well, guess what? You're close. You're very close. Oh, I see one more. Do you have another idea, or are you just stretching? Gentlemen. It's okay. So, what do you know about, one of you said something about cream was in it.
What? We're getting feedback.
Yeah,
What?
it's cutting it out. It cut in and out, so we didn't catch the question.
Oh, the water got more dense when the cream was in it. That was what one of your classmates said.
Mm-hmm.
Okay. Can you give me a little more information on that? What's making it dense?
Okay, stand up, Sarah.
When the drops are mixed into the water, she said there were some kind of cream drops, and cream is really thick. At least that's kind of what it is. And if it's added to water, the light probably would travel through the cream mixed with the water, as well as less of the cream. So pretty much the light is getting caught.
Okay, that's true for the bottom, but the light on the side was increasing.
It was increasing because the light wasn't traveling all the way to the bottom, so it was being held up in the top to the point where so much light was up there that more light was given to the side.
Okay, so do you guys know the term molecules?
Yeah.
So is it fair for me to say that you think the molecule of the cream might be bigger than a molecule of water?
Yes.
Okay, so there's actually something going on inside the jar that is just like what happens when light comes from the sun to the earth, and that's called scattering. The light is hitting those big molecules of cream, and it's being shot out in different directions. Does that make sense?
Yeah.
So it's being scattered in different directions. So we have a diagram to show you, and I want you to look at this diagram and tell me how this diagram is like our experiment.
All right, that's my part. So I'm doing, here we go. There's a diagram.
Okay, it's still loading for me.
Michael, can you guys see that?
Yeah, we can see it.
Okay.
Great. So look at the diagram and tell me how this is like our experiment that we just did.
We took cream and water and then we put it together like the sun. We detected on the satellite and then we scattered light.
Okay, I couldn't understand what you said.
Okay, well, I'll get back to him when Kira finishes.
Sun going down, it scatters, like when the flashlight went down and hit the cream, it scattered and it created more.
Okay.
Anybody else see any similarities? Danny, give me a thought. Any thought? Go. Stand up, please. Okay. Right. So in the bottle, the cream was making it scatter. What's making it scatter? What's making the light scatter in the diagram? Alexa.
When the sun is coming down, the center satellite is the light of the sun. It's the light.
Okay.
Okay. All right.
So,
It's kind of what Alexa said, but when the sensor on the satellite, and the sun, rays reach and meet with each other, the light is scattered out and
so
Go ahead, Ginge.
all right. So essentially, can you guys hear me okay?
Yes.
Okay. The flashlight in our experiment represented the sun, the sunlight. Oh, hold on, let me get my earphones on. Okay. I'm still getting it back. Anyway, the sun is the flashlight. The sensor we took on the bottom is the ground-based sensor as the sun comes all the way through the atmosphere and gets to the ground. And then that side measurement that we did, the side reading, is the sensor on the satellite. It's basically picking up what is being scattered in the atmosphere back out or back into space. So when we want to look at what gases are in the atmosphere, dust, particles, even gases like pollution or ozone, we look at what's being scattered. If anyone's seen a Google map or Google satellite view, they don't want the stuff in the atmosphere scattering the light. They want a nice clean image of the Earth, and the light bounces straight back out, like the clear bottle in the very beginning. The more stuff, the less of a good signal you're going to get bouncing back off of Earth. So this brings us back to why is the sky different colors? Can anyone have any thoughts about how this experiment maybe relates to back to our colors?
it makes the color of the sky change.
Yeah, like what did we just learn about the scattering of light might have to do with the color of the sky?
Just what you think. We're not expecting you to know for certain. Give a thought, Elsa. What do you think this has to do with the color of the sky?
I think I know.
Just anything. Say anything and then throw it. No?
It matters on the position of the sun. Wherever the sun is, in a certain position that affects the light, and you can use this for the sky.
Okay. Did we change the position of the flashlight?
That's part of it. So I have a quick movie that I'm going to play. And then we're almost near the end, but this will kind of help bring it home. And I'm going to unplug this, and hopefully we can hear this okay. Can you see the movie?
We're seeing why is the sky different color slide.
Okay, I'm trying to show the movie. Oh, wait a minute, hold on. I might have to share a different screen. Switch screen or window. I'm getting it. This whole technology thing.
Oh, there we go. Yeah,
Awesome.
we can have that.
Okay, here we go. It's going to be like a little 20-second thing.
Scientists can learn the composition of an atmosphere by considering how atmospheric particles scatter visible light. Earth's atmosphere, for example, generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to scatter energy with the wavelength of blue light. When the sun is low in the sky, however, light travels through more of the atmosphere and more blue light is scattered out of the beam of sunlight before it reaches your eyes. Only the longer red and yellow wavelengths are able to pass through, often creating breathtaking sunsets. When scientists look at the sky, they don't just see blue, they see clues about the chemical composition of our atmosphere. However, visible light reveals more than just composition. As objects grow hotter.
Okay, I'm back. All right, I'm coming back to my window here, my slideshow. So essentially what we're learning is that color, here we go, I'll show the screen. So basically light is made up of the colors of the rainbow. I think we kind of talked about that earlier. And the colors of the rainbow are split apart because they're different wavelengths. So if we look at blue, it's a smaller wavelength, and red is a longer wavelength. So when we have a clear blue sky, like the video said, it's those oxygen molecules that are scattering, like we saw with the milk, scattering the blue waves because they're very small. As the sun goes down and you get a sunset, the sun is actually going through more of the atmosphere, so more of the blue is being scattered out, more of the green is being scattered out, and only the red gets through, and that's why it looks really red. So we're basically able to look at, here's our thing, different parts of the electromagnetic spectrum. Move this. We just talked about the visible, where we have red light, green light, blue light. The wavelength of blue light, you can see there, is about the thickness of the bubble, a skin on the bubble. Not the size of the bubble, but the thickness of the bubble membrane. And as we get to smaller wavelengths, into ultraviolet, past violet, about the diameter of like of some molecules or rhinovirus, we can, this is light we can't see. Someone said it's purple, kinda, if it's right on the edge of visible, but it goes off into ultraviolet. It goes beyond what our eyes are able to see. Bees and some animals are able to see in ultraviolet. So if we looked at what's scattering ultraviolet in our atmosphere, let's see, there we go. We can actually see gases that are not visible to our eyes. So this is actually nitrogen dioxide, and that is being scattered by basically scattering UV light. So if I had like a UV light flashlight and I was putting it through a bottle full of nitrogen dioxide, that would scatter it. Okay, and I think that's it. This is the last one that's basically another gas in the atmosphere called ozone. If anyone's heard of the ozone hole or the ozone layer, this is what protects us from the UV radiation. And the UV, really high energy UV or UVB that gives us sunburn, basically interacts with ozone molecules, and that's a good thing because it absorbs the UV so it doesn't get down to the surface of our planet and give us a sunburn. So I think we're running full on time, so I'm going to kick it back to Michael. If anyone had any questions or if you need to wrap up because you're at the end of class.
Any questions? No? We seem to be good on this end. We appreciate it.
All right, thank you.
Thank you. Everybody wave bye.
Bye.
That was awesome. We appreciate it. Thank you. Not like that. Crazy. Thank you.
All right, thank you. Hey, Aaron.